Hello, I'm Gage Grindstaff, and Kyle Gross and I will be presenting on a paper published by a team in China in the Chemical Engineering Journal titled Novel Nanofiltration Membrane Prepared by Amphiphilic Random Copolymer Packing for High-Efficiency Biomolecule Separation. In essence, this paper discussed a membrane that has potential to be used in the separation of biomolecules.
As chemical engineers, we focus a lot on the separation of different substances. We have entire classes focusing on how to separate different compounds, but one thing that can be easy to forget when focusing on separating different chemicals is that if there is no use for the chemicals that we are separating, then there is no reason for us to separate them in the first place. The first thing that you should look to when designing a separation system is the products that you want. In the case of the pharmaceutical industry, two of the most important molecules that are needed to be isolated are amino acids and peptides. These two very small molecules are nearly omnipresent throughout the pharma industry, being used on drugs from chemotherapy to vitamin supplements that you or I may take every day. The usage of these two types of molecules is so large that I would not be able to list all of the drugs that are vital for in the time that we have. So this is why it is so important to mitigate the issues of these compounds have with separation.
Because different amino acids and peptides have such small changes in their structure and molecular weight, it is necessary to be extremely precise when separating them. This has resulted in many separation schemes to isolate needed molecules having numerous issues. The commonly used contemporary technologies for separating amino acids and peptides are highly varied, but the most common are centrifugation, adsorption, chromatography, and electrophoresis. While all of these technologies are different, they have the same general problems. They are high cost and low productivity, which means that it is tough to use these technologies in large-scale production. The problems caused by these technologies have created the opportunity and need for a separation scheme that is lower cost and higher efficiency for this application. A membrane fits that criteria perfectly. While membranes are tough to develop and need to be researched, as opposed to the earlier technologies I listed, once it is in use, it is easy to operate at a low cost, and if designed correctly, high efficiency with the ability to be scaled to larger operations. The nanofiltration membrane, or NF membrane, fits the needs of the industry perfectly.
This process begins with the goal of synthesizing a nanofiltration membrane using a soap-free emulsion method to pack amphiphilic random copolymer nanoparticles. Unlike traditional emulsion polymerization, this method avoids surfactants, which reduces contamination and improves membrane compatibility for biological applications. The synthesis involves copolymerizing two key monomers, N,N-dimethylaminoethyl methacrylate (DMC) and methyl methacrylate (MMA) in water using free radical polymerization. Due to their amphiphilic nature, these monomers self-assemble into micelles in the aqueous phase. These micelles act as the building blocks for nanoparticles, which are later used to fabricate the nanofiltration membrane. After nanofiltration synthesis, the particles are packed and thermally annealed to form a defect-free, high-density membrane structure. From this process, three distinct nanofiltration membranes are produced, each classified based on their DMC content. First is the 1.25 DMC-PES, contains the highest DMC ratio, which increases hydrophilicity and surface charge. Second is 0.75 DMC-PES, has a medium DMC content with balanced filtration and charge properties. And the third, 0.25 DMC-PES, which has the lowest DMC content, leading to reduced hydrophilicity and weaker charge interactions. So these three variations allow for tuning for membrane separation properties for different biomolecules by altering the copolymer composition. To evaluate the performance and structural integrity of the nanofiltration membranes, several advanced characterization tools were employed. Each method played a critical role in confirming nanoparticle properties, membrane morphology, and separation behavior. The first technique used was dynamic light scattering, DLS, which measures the particle size distribution and hydrodynamic diameter of the nanoparticles in solution. This step is critical to ensure that the polymer nanospheres fall within the optimal range for uniform packing during membrane fabrication. Transmission electron microscopy, TEM, then was used to visualize the internal core, shell structure, and morphology of the nanoparticles. These high-resolution images helped verify that the self-assembled micelles formed correctly and consistently. Next, scanning electron microscopy, SEM, was utilized to examine the membrane surface and cross-sectional structure. This analysis provided insight into nanoparticle arrangement, membrane thickness, and pore uniformity, which are all essential indicators of membrane performance. Zeta potential measurements were also performed to determine the surface charge of both the nanoparticles and the resulting membrane. This data is important for predicting interactions between the membrane and charged biomolecules, which directly impact filtration efficiency. Lastly, UV spec was used to measure absorbance at specific wavelengths to determine protein concentrations in both the feed and permeate solutions. These values were used to calculate the membrane rejection efficiency and assess how effectively it separates between biomolecules.
The first thing that was tested when discussing the membrane was the synthesis of it. As was discussed earlier, the membrane is created through a complex process of combining a DMC and MMA molecule while facilitating the creation of micelles. It would be important then to determine the best circumstances for generating the micelles that will develop into the final membrane. This is the focus of both figures 1 and 2. Two variations were made to test their effects on generation of micelles, changing the ratio of DMC added to MMA added, and by changing the solvent between water and ethanol. Figure 1 shows the micelles generated within these different systems. These pictures, taken using the SEM and TEM methods discussed earlier, along with the dynamic light scattering, allow for the measurement of micelles in the different conditions, which allows for the graphs within figure 2 to be compiled. Unfortunately, the DLS method that is used to measure these sizes can lead to swelling within the micelles that will not be present in normal circumstances. This is shown in parts A and B of figure 2, but overall the error coming from this was determined to be insignificant due to the obvious trends that are shown in part C of this figure. Part C is the real star of this figure and tells us a few important things. While the sizes of the micelles were very similar at low concentrations of DMC in both water and ethanol, they had opposite trends when the concentration was increased. As concentration increased in water, size increased, while in ethanol, size decreased. This trend leads to the conclusion that ethanol with higher concentrations of DMC is the most optimal path to take when creating the membrane, as smaller micelles result in tighter packing and smaller pore sizes that are desired within the membrane.
This graph illustrates the zeta potential for membrane types across the pH range of 3 to 10. The PES membrane, shown in black, exhibits a decreasing trend in surface charge with increasing pH, even crossing the 0 point and becoming negatively charged above a pH of 4. This indicates low and unstable surface charge, which contributes to weak electrostatic interaction with the biomolecules. In contrast, the DMC-PES membranes show significantly higher positive zeta potentials across the entire pH range. This increase in surface charge is attributed in the incorporation of DMC monomers, which introduce amine groups that remain protonated under neutral and acidic conditions. The 1.25 DMC PES membrane displays the strongest positive zeta potential overall, suggesting it will have the highest affinity or negatively charged biomolecules. This enhanced positive surface charge directly contributes to improved membrane solute interaction through electrostatic attraction, making the DMC modified membranes more effective for biomolecule separation, particularly at lower pH values.
To further look at the performance of the three different membranes, we can look toward the next test that was performed on them, which was cataloged in figure 7. In order to start initial tests on how effective the NF membrane is on separating compounds, tests were run to see how effective the membrane would be at separating various salts. Salts were chosen because of their various similarities to the final goal, amino acids and peptides. The salts chosen are of similar size to the common amino acids and peptides that would be separated, and just as importantly, they have similarly varying charge properties that the membrane can use to separate them. The data collected for this separation supported the understanding of the membrane as one that operates on both size and the charge of the molecules. The two most rejected salts, magnesium chloride and calcium chloride, are not only the largest molecules, but also have the largest electrostatic interactions with the membrane. By contrast, sodium chloride and especially magnesium sulfate are a bit smaller and vary significantly in their electrostatic interactions with the membrane. This lends itself to the fact that the NF membrane will most likely be able to separate amino acids and peptides that largely are very similar in size, but different in charge. The other conclusion that can be taken from this data is that, as was indicated by the graph on the previous slide, the 1.25 DMC PES membrane seems to be the most effective separator. Though on the graph the differences seem minimal, and they are, these are still significant enough for the researchers to conclude that it is more effective than its alternatives in most cases.
Now that the initial separation testing has been done, we can move on to Figure 8, which is really the final proof of the efficacy of the NF membrane and that it may solve the problems with the current separation methods that are explained at the beginning of this presentation. Now that the membrane has been put through all the prior tests, in order to test if it is actually viable for separating amino acids and peptides, 2 of each were put through the membrane. For the peptides, this was GHL and GGL, and for the amino acids, lysine and glutamate. These were chosen specifically for the difficulty of separation, having very similar or identical molecular weights, but different charge properties. The efficacy of the membrane was tested while varying the concentration and the pH of the feed. Concentration was tested in order to determine whether the membrane works better with a high concentration or a low concentration feed, while the pH was varied for similar reasons. We mentioned earlier when discussing Figure 5 that pH has a significant effect on the electronegative interactions between the molecules in the membrane, and as it can be from the resulting data, pH indeed does have a significant influence on the rejection percentage of the molecules, specifically for the peptides. Variation in the concentration were much less influential but still significant. It was determined that for the separation of both types of molecules, a slightly basic solution with a low concentration of a desired molecule is ideal, but for the amino acid separation allows for more variation conditions while still allowing for good separation. The large problem for the NF membrane can also be seen in this data, that the selectivity for the desired molecules is relatively low, hovering between the low to mid-20s. While this is consistent with other types of membranes, both in research and commercially available, it is still the largest problem facing in the NF membrane and being used as a widespread separation scheme for peptides and amino acids.
When leaving this paper, there are a few important things to take away. The first and most important of these is that the NF membrane is a viable method for separation of amino acids and peptides, with many advantages over the current methods used to separate them, meaning that it has fulfilled the motivation behind the experiment mentioned at the beginning of our presentation. This is a significant accomplishment and should be the largest takeaway from the paper, but that does not mean that there are not still negatives with the membrane. While cost is low and separation is precise, the selectivity of the needed molecules is still relatively low. This is a significant downside to the membrane, especially in a large-scale operation that may prevent it from replacing its contemporaries as the most commonly used separation scheme for amino acids and peptides. The other two takeaways that we want to emphasize are less important to the feasibility of the membrane and closer related to its production and operation. While they may be less important to someone deciding to use the membrane, they will be vital to someone using the membrane. The first of these is that the production of the membrane can be optimized when produced in an ethanol solution with high concentration of DMC. This is not only important for production, but also to future improvements, giving future studies a good place to start in looking to improve the membrane. The forward-facing approach can also be applied to our final takeaway, that for most applications, the 1.25 DMC PES membrane is the most effective. For someone looking to implement, this is a great thing to know, and hopefully this particular version of the NF membrane can be further improved so that it can completely solve the difficulties that face amino acid and peptide separation in the future. Thank you for your time.